binary in the center of a star cluster where there's a bunch of other black holes and stars that are sort of moving around in space. And essentially what I've done is create effectively a particle physics experiment. I have some giant target with cross-section roughly proportional to the semi-major axis squared hanging out, and I'm going to continually bombard it with other particles. Now, if you're, particularly QFT inclined and just a little bit insane, you can actually express this in terms of Feynman diagrams. You can write down the various encounters and their probabilities using essentially interaction diagrams. It's very pretty to put on a slide. It's pretty much useless when it comes to doing actual calculations, but I like to throw it up there to convince physicists that I'm doing real things. In reality, the easy way to do this is just to put it into a in-body integrator and actually crank the outcome. So in this case, I'm directly integrating the Newtonian equations of motion, and I'm throwing a binary to single star. And what happens is, even though this is a formally chaotic process that you can't analytically solve, it's still something that's pretty easily solved on a computer. And so this is basically what we do. We fire different objects at one another in a large-scale cluster and look at what happens in the outcome. And you can see already right here that two very interesting things happen during this encounter. One is you've exchanged one of your partners. So the sort of cyan black hole has kicked out one of the orange black holes from the pre-existing binary. It's what we call an exchange interaction. The other thing that's happened is that if you look at this, you can actually see that the orbital period of the binary that was created in this exchange process is actually smaller than the orbital period of the binary that went in. This is actually essentially a statistical property of these clusters. It's something called Hagees Law. Essentially, as long as your binary has a greater binding energy than the typical kinetic energy of particles that are bothering it, on statistical average, you will characteristically shrink the orbit of the binary and liberate some of that potential energy into kinetic energy of the recoil.
It's rules of marriages.
Say what?
Human relations.
Also, yes, there's a whole list of analogies you can make to different relationships with this, but this is probably not the right talk for that. Anyway, so I have this binary that undergoes a hardening encounter. It shrinks its semi-major axis, gets a faster orbital period. It also converts some of that potential energy into recoil, so it gets kicked out into the halo of the cluster. Once it's out there, a process called dynamical friction will slowly bring it back into the center, where it again interacts with another black hole, shrinks, and gets kicked out into the halo again. This process continues sort of inevitably until one of two things happens, and it's a question of timescales at this point. So I have two competing timescales going on during each one of these encounters. There's the gravitational wave merger timescale. Basically, how long is it going to take gravitational waves to drive this binary to merge? If you're, again, feeling particle physics-y, you can think about it as the decay timescale for this particle. And then there's the time between successive binary and single encounters. How long, in a mean-free path sense, is this binary going to travel through the cluster before it encounters another particle? Now, if the gravitational wave merger timescale is much, much less than the binary single timescale, then this binary is going to essentially merge in the cluster. So it's going to create a new black hole with roughly twice the mass and a spin of 0.7. And if you're lucky, and that's what I'm going to be talking about for the last 19 minutes, that remnant product gets to stay in the cluster. On the other hand, if your gravitational wave merger timescale is much longer than your typical timescale between successive encounters, then eventually one of those encounters is going to have a sufficient recoil kick that it completely ejects the binary from the cluster, where it may or may not merge later on in the field of the galaxy. Now, roughly speaking, I've done a lot of work on trying to figure out what the different properties are of the binaries that merge in the cluster or outside of the cluster, and whether or not there are different observable properties. And it actually does turn out that the in-cluster mergers do tend to have higher orbital eccentricities. It's essentially a selection bias. Higher orbital eccentricity gives you a lower gravitational wave timescale, so those are more likely to merge in the cluster. But that's not what I'm going to be talking about today. The upshot of this that is important to keep in mind for this talk is it's a roughly 50-50 split. About half the binaries merge in their cluster, and half the binaries are kicked out into the field where they may or may not merge later on, depending on what their properties are. And so for those ones that merge in the cluster, like I said, you have this black hole, creates a new black hole with, give or take, twice the mass and a dimensionless Kerr spin of 0.7. And the question is, do you actually retain this merger product in the cluster? Now, for the longest time, we thought the answer was essentially no. Like, people have been thinking about this particular process, successively merging black holes in star clusters for at least 20 years, and probably a lot longer than that. And the answer that people used to say was that no, you don't retain these black holes in the cluster. And the reason has to do with the way gravitational waves are emitted during a binary in spiral. So if I take, for instance, the typical, if I want to know what happens to a binary when it merges, I can ask, essentially, what kind of kick does that binary get when it merges? And the kick actually comes from the binary, from essentially the orientation of the binary spins. So let's say I have a binary black hole with an angular momentum this way and 2 spins at, say, about 45 degrees off of the angular momentum axis. This configuration is what we typically call a superkick configuration. It turns out that when your spins are aligned at about 45 degrees off of the orbital angular momentum, you have a preferred direction for the emission of gravitational waves. In this case, it's sort of shooting out the bottom of the binary like a rocket. I actually don't know if that's exactly the direction to come in, but it happens to be the best that works for the picture. But the point is, you're converting a huge amount of this gravitational waves in the rest mass of these objects into gravitational waves. And in that process, you're essentially creating a huge amount of mass energy and momentum transfer into gravitational waves. And if the spins of all your black holes are roughly extremal, so they're spinning at a curve parameter of 1, you can get kicks as large as 5,000 kilometers a second. If I plug in typical numbers for what I would expect in a cluster and just randomly pick spin directions on the sphere, most merging binaries will get a kick of about 1,000 kilometers a second.
Question?
Yeah.
You have just like a charged particle moving in a circle. I thought it kind of wanted to radiate out in the plane.
Yeah,
this looks rather counterintuitive, isn't it?
So it has to do with the fact that the spins are off from the orbital angular momentum. If there were no spins in the black holes, then essentially it would actually be, I'm not sure if it's planar, but it's spherically, it's symmetric.
Well, if there are no spins, it's basically the 2 black holes come within their last stable orbit, ISCO, and then they just plunge.
Yeah.
If there are unequal masses, you get the anisotropic emission in one of the directions, but it's actually the direction of their plunging. That,
exactly, yeah.
But
So
isn't the spin a higher order correction to the quadrupole moment? I mean,
it is, but I mean, this all happens in the last few orbits. At that point, you're into essentially the weeds of the post-Newtonian expansion. I mean, this emission pretty much occurs, like Avi said, right at the plunge, which happens right at roughly the ISCO of the orbits. So all of this emission, because otherwise, right, it wouldn't matter. You're moving around in the quadrupole approximation, but it's like mass loss from a binary. You're essentially spinning out in every direction, so there's no net momentum gain. But the asymmetry happens at essentially the last few orbits, because at that point you plunge, and you just have essentially this last burst of gravitational waves. What you really need, though, is something to break that symmetry. Did that make sense?
I mean, you said it was hard to calculate, but I don't understand why it would be. I mean, like in M87, right? We think most of it's going out to the side. Is that right?
You mean the
You mean
jet?
that?
What do you mean in magnetism?
The radiation.
But that's a jet. Here it's gravitational waves.
So that's
This is like a.
So this is gravitational waves from a merging binary, though. So unlike M87, where you can essentially assume that you have a single mass in the center and that everything's essentially moving in the test particle limit around it, in this case, you actually have to solve this. Like, all the stuff we know about this mostly comes from numerical simulations. The way I've done this, for instance, is actually taking fitting formula to numerical simulations. Because you really need to know what's happening to the radiation emission during that last orbit.
Well, if you take a wet object and spit it around, like the water will spray out in the plane, right? So,
Yeah.
So the intuition would be that things go out in the plane. Now you're telling me that the problem becomes strongly coupled and we can't use our intuition, but it's collimated
Well,
in exactly the opposite way? Is there
when
any
you have
intuition that goes along with that?
I mean, well,
I'm
an easy
not
way to-
questioning it's true, it's just.
Well, let me put it this way. The plane is not the plane when you have spins. So, because of spin-orbit coupling, the actual the total angular momentum is conserved. Actually, no, it's not even that, because you have gravitational waves. But essentially, the plane of the orbit starts precessing around the total angular momentum of the system. So the plane of the orbit itself is even moving as these things are merging. And by the time you get... Gravitational waves shrink the angular momentum of the binary, they don't shrink the angular momentum of the spins. So by the time you're about to merge, the spin angular momentum is actually dominant over the orbital angular momentum as far as your total angular momentum budget goes.
But in this picture, it points in the same direction, right? If you sum
Yeah.
those two red arrows, it points in the same.
Yeah, the Superkick configuration, as it's called, is, and I don't have a good physical intuition for why this is true, is that if you have 45-degree misalignment between the orbital and spin angular momentum, and that they are anti-aligned with one another. So they're pointing essentially in this direction, and the, I don't have enough fingers for this, the orbital angular momentum is going that way. I don't have a good physical intuition for why that is, sorry. But in any case, the upside of this is that the escape speed from most clusters is, especially globular clusters, is around 100 to 10 to 100 kilometers a second, give or take. Nuclear star clusters can go higher, but even then, it's only about maybe 1,000 kilometers a second. Most of your kicks can get up to several thousand kilometers a second. And so you're essentially going to eject all of these binaries from the cluster during merger. So you have this merger product, it gets a huge radiation recoil kick when it merges, and it gets ejected from the cluster. And we were fine with this for a while. We thought for the longest time that you could actually use the spin orientations themselves as a way to discriminate between formation channels. As an example, LIGO, for instance, can't measure the spins themselves very well, the individual spin components, but they can measure the projection of those spins onto the orbital angular momentum. It's what they call the effective spin parameter, or chi-effective. And you can see right here that this is the posterior from one of the first 10 LIGO events, and they constrain really well the amount of spin that is projected onto the orbital angular momentum. And so we were kind of fine with this for a while because we thought we could use different measurements of chi-effective to distinguish between different formation channels. You would expect different spin orientations for black holes born in a binary versus black holes born in a dense star cluster.